Every year, over 50 million tons of electronic waste are generated worldwide, a weight greater than all the airplanes ever built by man. Some of this equipment disappears into the shadow market, while another part goes to legal centers where gold, copper, and palladium are extracted from it. But what happens to your old laptop after you turn it in at a collection point? Where do the hard drives with personal data disappear? And how is pure gold of 99.9% purity born from a pile of scrap? Watch until the end, and you will find out what the most profitable side of electronics disposal is hiding. In many cities, there are stationary or mobile points where people can bring old devices. They are often organized by municipalities, environmental organizations, or the recycling companies themselves. These points can be located in shopping centers, near supermarkets, or on separate sites. Campaigns and promotions are regularly held, during which large retail chains or electronics manufacturers organize temporary collection points. This encourages people not to throw away e-waste, but to turn it in for recycling. Some companies offer services for picking up old electronics directly from homes, especially when it comes to large devices like refrigerators or televisions. Large volumes of electronic waste come from companies, offices, educational, and government institutions. When companies update their computer fleets, servers, telecommunications equipment, they enter into contracts with specialized disposal companies. This allows them to comply with environmental standards and ensure the secure destruction of data. For a business, the destruction of confidential information from hard drives and other media is extremely important. Recycling companies often offer services for certified data destruction before recycling. In many countries, there are laws that require electronics manufacturers to be responsible for the life cycle of their products, including their disposal. Write now in the comments from which country you are watching us. Manufacturers can pay contributions to special funds or organize their own collection and recycling systems. This encourages them to develop products that are easier to recycle. They cooperate with recycling enterprises that are part of their network, ensuring a flow of used electronics. Scrap metal collection points. Although not specializing exclusively in electronics, some scrap metal collection points also accept electronic devices, considering them as a source of metals, including precious ones. However, this path often does not ensure optimal recycling and can be less environmentally friendly. Unfortunately, there is also a shadow market. Significant volumes of electronic waste are illegally exported to developing countries, where they are disassembled in artisanal conditions, causing harm to the environment and human health. However, the legal recycling enterprises we are talking about operate within the legal framework. When the electronics are collected, they are transported to the centralized warehouses of recycling plants. There, they undergo initial sorting. Large batches of a single type of electronics, for example, only old computer boards or only mobile phones, can be separated to optimize the further processes of disassembly and extraction of valuable materials. Thus, a whole stream of electronic devices enters the warehouse of a recycling enterprise, ready for their valuable components, including gold, to get a second life. After the trucks deliver mountains of electronic waste to the recycling warehouse, the first and very important stage begins: manual disassembly. At this stage, teams of qualified technicians and operators work. This is not just breaking old devices. It is a systematic process aimed at maximizing the extraction of valuable components and separating hazardous materials. Each workplace is equipped with the necessary tools: screwdrivers of various types, pliers, wire cutters, as well as specialized devices for safely opening cases. Proper lighting and ventilation are also important, as some components may contain harmful substances. Workers must wear protective equipment, gloves, goggles, and sometimes respirators. The process begins with relatively light devices, such as laptops, desktop computers, and televisions. Specialists sequentially disconnect the main units. Lithium-ion batteries, found in laptops and mobile phones, are removed first. They are potentially flammable and contain valuable metals that require separate recycling. Printed circuit boards are one of the richest sources of gold, as well as silver, palladium, and copper. The boards are carefully removed from the cases. Central processors and RAM modules are especially valuable, as they contain significantly more gold than other parts of the board, so they are often separated for separate, more intensive processing. Each removed component is placed in a special container. For example, one container for printed circuit boards, another for processors, a third for batteries, a fourth for aluminum parts, and so on. This sorting is critically important, as it optimizes the subsequent stages of recycling. Components with a high gold content will be sent to more targeted and intensive extraction processes. After the initial manual disassembly and sorting, when components with a high gold content, such as processors, memory, and gold-plated connectors, have been separated, much more targeted and intensive processes for their recycling begin. These methods are aimed at the most efficient and economically viable extraction of the precious metal. They combine mechanical, chemical, and sometimes even electrochemical approaches. The first step is often further mechanical processing to further concentrate the gold-bearing material. Processors, for example, consist of a ceramic or organic case, metal contacts, and sometimes metal covers. These parts need to be separated. This is usually done with the help of special shredders or milling machines that allow for the separation of the metal legs or contacts from the main part. Some processors may be subjected to thermal shock to crack the ceramic case and release the gold-bearing parts. The separated gold-bearing metal parts are crushed into small granules or powder. This process increases the surface area of the material, which is critically important for further chemical processing. Usually, crushers are used, and then granulators, which grind the material to a fraction size in the range of 0.04 to 0.4 of an inch, and sometimes even smaller. After crushing, gravity separation may be applied, for example, vibrating tables, centrifugal separators, or hydrocyclones. Since gold is significantly heavier than most other metals and non-metallic impurities, these methods effectively separate fine gold particles from lighter materials, creating a more concentrated, heavy metal slurry. For large volumes of gold-bearing concentrates, especially if they contain a significant amount of copper or other base metals, high-temperature smelting is used. The concentrated powder or fine granules may first be sintered or briquetted for more convenient feeding into the furnace and to reduce dust losses. The material is loaded into special electric or induction furnaces. Temperatures can reach 2,500 degrees Fahrenheit. During smelting, lime or silica is added, which reacts with oxides and other non-metallic impurities, forming a low melting slag. Gold, like other precious metals, has a high affinity for molten copper or lead. Therefore, during smelting, gold dissolves in larger volumes of molten copper or lead, forming a so-called black copper or lead alloy. This alloy is then separated from the lighter slag. The alloy can then be further purified in converters, where air or oxygen is blown through the melt to oxidize the remaining base metals, which then pass into the slag. The output is an enriched alloy containing copper and all the precious metals. After removing the main part of the base metals, the material is treated with reagents that dissolve gold. After dissolving the gold, the solution is filtered to remove undissolved solid residues. Then the gold ions are separated from other metals using various methods. Gold is precipitated from the purified solution by adding reducing agents. These compounds reduce the gold ions to a metallic state, forming a pure gold powder. The gold powder is thoroughly filtered, washed with distilled water to remove residual chemicals, and dried. The resulting gold powder is melted in high-temperature induction furnaces and cast into ingots or granules. At this stage, high-purity gold is already obtained, often 99.9%. Every year, over 500,000 bridges are built worldwide, but only a few of them challenge nature and time. To create a giant capable of withstanding thousands of tons of steel, windstorms, and earthquakes, engineers first dive into the very heart of the Earth, drilling the ground to a depth of over 100 meters, studying every layer of rock. Here, under water and mud, the foundation is born, on which the fate of the entire structure depends. How do machines weighing as much as houses place piles with millimeter precision? And what will happen if even one of them shifts? Watch until the end, and you will learn what the engineering elite keeps silent about. The construction of long bridges begins long before the first steel beams or concrete supports appear. It all starts with a site investigation. Engineers analyze the soil, the strength of the current, the level of seismic activity, and the depth of the bottom, if it's a river or a bay. Often, special drilling rigs are used to take rock samples at depths of over 300 feet. These data determine the type of the future bridge: suspension, cable-stayed, or beam. After this, a three-dimensional model is created. It takes everything into account: the load from transport, the force of the wind, temperature fluctuations, and even the possible impact of waves during storms. For bridges longer than half a mile, the permissible error in calculations can be no more than a few millimeters. Otherwise, the structure may lose stability. When the construction of a bridge moves from drawings to the actual ground, one of the most responsible and complex stages begins: the construction of the foundation, or the pile foundation. It is these structures, hidden under water or earth, that support the weight of the entire bridge: thousands of tons of steel, concrete, transport, and even wind load. Drilling cranes arrive at the site, giant machines with a long mast, a hydraulic drive, and interchangeable drills. They can reach the height of a 3-story building. Steel piles are brought to the worksite. Usually these are pipes with a diameter from 3 to 6 feet and a length of up to 100 feet. In marshy or marine areas, the piles are even larger, sometimes up to 150 feet. The drilling process takes place in stages. The machine is positioned with an accuracy of a few inches. For this, laser and GPS systems are used. Then the operator lowers the drill into the ground. The powerful rotation of the bit crushes the rock, and a hydraulic system pumps out the resulting pulp. In some areas where the soil is unstable, drilling is carried out with the immersion of casing pipes, metal casings that prevent the walls of the well from collapsing. When the hole reaches the specified depth, a steel pipe, the pile casing, is installed in it. A reinforcing cage is lowered inside, which strengthens the structure, after which concreting under pressure begins. Through a special hose, a concrete mixture is supplied from the bottom up, displacing water or mud. Thus, a dense, air-free mass is formed, which over time hardens into a monolith. In marine areas, floating barges with drilling rigs are used. Divers control the position of the pile underwater, and engineers monitor the process with ultrasonic sensors. In a strong current, drilling is carried out only during periods of calm, when the wave level is minimal. When the piles are installed, their tops are cut to the required height, and capitals are mounted on them. Large concrete blocks that unite several piles into one support. After this, pylons or columns are erected on these foundations, which are already visible above the surface. On land, temporary sites are simultaneously set up. These are logistics centers where beams, cables, reinforcement, and concrete sections are stored. Often, huge cranes 300 feet high are used here, which can lift blocks weighing over 200 tons. When the supports are ready, the turn of the superstructure comes. For bridges of great length, two main technologies are used: suspension and cable-stayed. In a suspension bridge, the main load is carried by steel cables. To secure them, two massive towers, pylons, are first erected. Their height can reach 700 feet, as in the Golden Gate Bridge in San Francisco. The towers are assembled in sections, lifting each one with a crane and connecting them with bolts and welding. After the installation of the pylons, the main cables are stretched between them. This is a complex process that is carried out in stages. Thin steel wires, the thickness of a finger, are stretched one by the hundreds, until a main cable several feet thick is formed. Then vertical hangers are attached to these cables. They will hold the roadbed. In cable-stayed bridges, the main load is transmitted through inclined cables that go directly from the towers to the sections of the roadway. Such cables are made of steel strands with a polymer coating, capable of withstanding a load of over 500 tons. They are installed with the help of hydraulic winches, which precisely regulate the tension. The installation of the span sections is one of the most impressive stages in the construction of a bridge, when the giant engineering structure literally begins to connect the shores. Each section is a finished fragment of the road, made of high-strength concrete or steel at a specialized plant. There they are formed in giant molds, reinforced with steel bars, treated in thermal chambers for rapid strength gain, and then marked and checked for accuracy with a laser system. After this, these blocks are transported to the construction site. If the bridge is laid across a body of water, the sections are delivered by barges, floating platforms capable of withstanding hundreds of tons. On land, they are transported by multi-axle trailers with dozens of wheels, which evenly distribute the weight. The movement of such columns is usually accompanied by police, as each block can be from 100 to 400 tons and over 100 feet long. At the construction site, floating cranes or lifters are already waiting. These are powerful lifting systems capable of lifting a load of over 500 tons. Most often, such cranes are mounted on pontoons or mobile platforms that can accurately maneuver over the water. During the lift, the crane operator coordinates his actions with the engineers who are on the bridge supports. Every movement is a matter of inch precision, as the section needs not just to be lifted, but placed perfectly in the design position. When the block is suspended above the supports, it is slowly lowered. Workers fix the position with the help of special guide pins and laser marks. Then dampers and high-strength connecting bolts are installed in the joints of the sections. It is important that the sections fit together without the slightest misalignment. Even an error of half an inch can cause uneven load. Next, the joints are filled with cement mortar under pressure, which fills all the voids and forms a monolithic connection. In some types of bridges, post-tensioning cables are used, steel strands that are threaded through the internal channels of the sections and tensioned with hydraulic jacks, providing additional strength. If the bridge is being built over the sea, the installation is even more complicated. Barges with sections are tied to positions with an accuracy of a few feet using GPS, and the lifting takes place only in calm seas. Often at night, when the wind is weaker and the waves are minimal, the crane slowly lifts a section. The process can take several hours. From the side, it looks like a giant aerial operation. A steel or concrete slab, as huge as a two-story building, smoothly rises above the water or a gorge, moving with an accuracy of a few centimeters. When it is fixed between the supports, the bridge literally grows. Another span, another few tens of feet of road, which bring it closer to completion. In parallel with the installation of the roadbed, communications are laid, lighting systems, communication wires, pipes for rainwater drainage. Most bridges have sensors that measure vibrations, temperature, the tension of the cables, and even the concentration of salts in the air. These data are constantly transmitted to a control center. When the main structure is completed, the road surface work begins. The surface consists of several layers. The first layer is a special anti-corrosion compound that protects the concrete and metal. Next, waterproofing is applied, then several layers of asphalt or polymer concrete, about 4 inches thick. For suspension bridges, lighter materials are used to reduce the load. The final stage is the installation of railings, noise barriers, and the painting of steel elements. The painting has not only an aesthetic function, it also protects the metal from corrosion. For bridges over the sea, paints with the addition of zinc are used, which create a stable protective layer. After the completion of all work, the bridge undergoes a series of tests. Special trucks are loaded onto it to check how the structure reacts to weight. Vibration tests are also conducted. Engineers check how the bridge behaves during wind or the movement of trains and cars. If the indicators meet the standards, the object is put into operation. Imagine, glass that once shattered into deadly sharp fragments now saves lives. How did humanity transform a fragile substance into armor for a car? And what is hidden behind this seemingly simple transparency? Every year, over 100 million square meters of automotive glass are produced worldwide, enough to cover the area of an entire country. But the real magic happens where molten stone is transformed into a perfectly smooth surface, in furnaces that reach temperatures of over 2,700 degrees Fahrenheit. How did ordinary quartz sand become the foundation of safety technology, without which we cannot imagine modern transport? Watch until the end, and you will learn what accidental experiment changed the history of automobiles forever. The history of automotive glass production is closely linked to the development of the automotive industry, which emerged at the end of the 19th century. The glass used in cars today has come a long way in improvements, making it safer, stronger, and more functional. When the first cars began to appear, they were initially not equipped with glass at all. The open body design only partially protected passengers, and dust, wind, insects, and other hazards made trips very uncomfortable. Later, as cars became faster, the need to install protection for the driver and passengers arose. The windshield began to be made from ordinary window glass, which, although it provided some protection, had a serious drawback. During accidents, it shattered into large, sharp fragments, leading to numerous injuries. The first revolutionary discovery in the field of automotive glass was the creation of laminated glass. This happened by chance. In 1903, the French chemist Edouard Benedictus accidentally dropped a flask with a nitrocellulose coating. The glass cracked but remained whole thanks to a thin layer of plastic. This accident inspired the scientist to create multi-layered glass, which later became the basis for triplex. Already in the 1910s, laminated glass began to be used in premium class cars. Its construction consisted of 2 layers of glass, between which a thin, transparent film was placed. In the event of an impact, the glass did not shatter, and the cracks remained on the film. In the 1920s, laminated glass began to be actively used in the production of windshields. Its main advantage was increased safety. Even during serious accidents, the fragments did not fly apart but remained in the polymer layer. The next stage in the development of automotive glass came in the 1930s, when the technology for producing tempered glass was patented. This material was produced by heating glass to high temperatures followed by rapid cooling. As a result of this process, the glass became stronger, and when it broke, it disintegrated into small pieces with blunt edges, which minimized injuries. In the mid-20th century, tempered glass began to be used for the side and rear windows of cars. It was cheaper to produce compared to triplex and provided a sufficient level of safety for these parts of the car. In the 1950s and 60s, automotive glass became even more perfect thanks to the development of technology. During this time, various important changes took place. Improvement of triplex. The development of new polymer films made laminated glass more transparent, resistant to ultraviolet radiation, and durable. Mass production. The automation of production processes allowed for a reduction in the cost of automotive glass, which made it more accessible to the mass market. Sun protection coatings. For the first time, special coatings began to be used that blocked ultraviolet light and reduced the heating of the car's interior. One of the most important technological breakthroughs in glass production was the invention of the float method in 1959. This technology, developed by the British company Pilkington, allowed for the production of perfectly smooth glass by spreading the liquid glass mass over the surface of molten tin. Thanks to this method, glass became more uniform, strong, and accessible for mass production. The float method is still the basis of automotive glass production today, ensuring its precise dimensions, surface smoothness, and high quality. In the second half of the 20th century, automotive glass underwent even more changes aimed at improving safety and comfort. In the 1960s, heating filaments began to be installed in the rear windows of cars, which prevented fogging and freezing of the glass. In the 1980s, glass with special metal coatings appeared, which reflected sunlight and reduced the heating of the interior. Glass with ultraviolet protection. Thanks to the introduction of new technologies, automotive glass began to provide almost complete protection against harmful radiation. And then we begin the modern period of automotive glass production, which we will talk about now. And we will start with glass for cars. Automotive glass is divided into several types depending on its purpose and production technology. Windshield. Usually this is multi-layered glass, which consists of 2 layers of glass, between which a polymer film is located. Such a design ensures that upon damage, the glass does not fly into sharp fragments. Side and rear glass. Most often this is tempered glass, which upon impact breaks into small blunt-angled pieces, which reduces the risk of injury. Panoramic roofs or other special types of glass. Laminated or tempered glass with a special coating for protection against ultraviolet radiation is often used. The main components of glass are natural materials that are mixed in certain proportions to obtain the desired properties. Quartz sand is the main component of glass, which ensures its transparency. It must be extremely clean and contain a minimum of impurities. Soda is added to lower the melting temperature of the glass. Lime improves the mechanical stability and chemical properties of the glass. Additional additives used to correct color, transparency, resistance to ultraviolet light, and other properties. The raw material is cleaned, dried, and crushed to a uniform state. It is important that impurities that can affect the quality of the glass are maximally eliminated. After preparing the raw material, it is loaded into special furnaces for melting. This stage includes several important moments. Let's look at them together. Melting temperature. A temperature of about 2,732 degrees Fahrenheit is used to form the glass mass. In the melting process, the raw material turns into a uniform viscous liquid. Homogenization. The glass mass is mixed for an even distribution of components. This is important to avoid air bubbles or inhomogeneities in the finished product. Furnaces for melting glass are equipped with modern temperature control systems and process automation, which ensures high quality of the final product. After melting, the glass mass undergoes a forming process, which in modern production is most often performed using the float method technology. Feeding the glass mass, the liquid glass flows out of the furnace and onto a bath of molten tin. Thanks to the high density of tin, the glass mass spreads evenly over its surface. Under the influence of its own weight, the glass forms a perfectly even and smooth surface. By gradually lowering the temperature, the glass acquires hardness. At the exit of the bath, it can already be processed. The float method allows for the production of glass sheets with precise geometric parameters and high surface quality. After cooling, the glass sheets are cut according to the dimensions required for automotive production. Automated cutting machines ensure the accuracy of the work. To prevent the formation of cracks and chips, the edges of the glass are ground. Each sheet is checked for defects, such as microcracks, bubbles, or other damage. Next, to ensure the strength and safety of automotive glass, it is subjected to a tempering process. The glass is heated to a temperature of about 1,112 degrees Fahrenheit. Then, the surface of the glass is rapidly cooled by streams of air, while the inner layers cool more slowly. As a result, stress is created, which increases impact resistance. Tempered glass, when destroyed, breaks into small, safe fragments, which minimizes the risk of injury. Next, for the windshield, triplex is used, a construction of glass and polymer film. Its production includes several stages. Joining the layers. A polymer film is placed between 2 glass sheets. The construction is placed in a vacuum press to eliminate air bubbles. Next, the glass is heated in an autoclave to a temperature of 284 Fahrenheit under high pressure. This ensures a strong connection of the layers. Triplex has high impact resistance, and upon damage, it remains in the polymer film, which ensures the safety of the driver and passengers. Next, to improve the properties of automotive glass, various coatings are applied to it. Anti-reflective coatings reduce glare from the sun or headlights of other cars. Ultraviolet protection. Special layers block harmful ultraviolet radiation. Hydrophobic coatings ensure that water runs off the surface of the glass. heating elements. Thin heating filaments can be embedded in the windshield, which facilitate the removal of ice or fogging. To achieve the desired shape, special thermoforming installations are used. The glass is heated to a temperature at which it becomes plastic and is formed according to the given parameters. And so, we have reached the final stage. During it, each product undergoes a thorough check. Transparency and the presence of defects are checked. Next, the glass is tested for impact resistance and endurance to loads. Compliance with standards. The accuracy of dimensions, shape, and other parameters are checked. Then the finished automotive glass is packaged in such a way as to avoid damage during transportation. It is delivered to car factories or service centers, where it is installed in vehicles. The production of automotive glass is a high-tech process that combines physics, chemistry, and engineering. Thanks to modern technologies and strict quality control standards, automotive glass ensures safety, comfort, and durability. And just imagine how many stages the automotive glass had to go through for us to be able to monitor safety on the road and have the opportunity to admire the wonderful landscapes. It seems incredible to me. And you? Every year, over 900,000 aircraft engines are manufactured worldwide, hearts that push giants of the sky on journeys across continents. But have you ever wondered how this metal monster is born? One that operates in conditions of over 2,000 degrees and at speeds that could destroy any metal. Inside it, titanium bones, a nickel heart, and composite lungs. And then, technologies resembling alchemy, single crystals, vacuum casting, and 3D metal printing. But the main secret is not in how it's created, but what's hidden inside. Watch until the end, and you'll learn something that even Boeing engineers keep quiet about. The turbofan engines that push giants of the sky, like Boeing and Airbus planes, resemble something out of science fiction. However, they are a true embodiment of engineering genius. How are these amazing machines assembled from tens of thousands of parts and ingredients, like a puzzle? Ordinary metals are not suitable for their manufacture. After all, the engine must operate in conditions where the temperature can exceed 1,800 degrees Fahrenheit. This is a real inferno, and ordinary steel simply wouldn't withstand it. This is where titanium alloys come on stage. Lightweight, strong, and able to not melt in extreme heat. And for the hottest zones of the engine, nickel-based superalloys are used. By the way, this isn't just metal, it's 21st century alchemy. Composites, particularly carbon fibers, are used for the fan to reduce weight while maintaining strength. Such a high temperature arises from the process of burning fuel in the combustion chamber, one of the most important elements of a turbofan engine. During engine operation, aviation fuel, usually jet fuel, is mixed with air and ignites, forming hot gases. These gases are literally accelerated to insane speeds and temperatures, over 1,800 degrees Fahrenheit, and sometimes even up to 2,700 in modern engines. This level of heat is needed to get the most efficient thrust. That is, the hotter and faster the gases, the stronger the energy flow that spins the turbine and provides the aircraft's motion. And here lies the main challenge. The engine must not only withstand these extreme conditions, but also operate stably, without the slightest failure. That's why it uses super technological materials, like titanium alloys and special composites, which can withstand both high temperature and insane mechanical stress. You know what's incredible about the process of creating an engine? That even individual parts, like the turbine blades, are created with micron precision. For example, the blades are cast in a vacuum so that there isn't even the smallest crack inside. Some of them are formed to have a single crystal structure. That's when a piece of metal has no seams at all. But that's not all. 3D printing? Yes, that's used too. For example, for complex parts that are impossible to make with traditional casting. The turbine blades are the heart of the engine. They operate in the hottest zone and convert the energy of the hot gases into rotational motion. First, a model of the blade is created from wax. Yes, it looks almost like artistic sculpting, only here, precision down to the micron is important. This wax sample is then dipped into a special ceramic solution, which gradually dries, forming a strong mold. This mold is like a perfect cast of the future blade. The wax inside is melted and removed, and the ceramic is ready for the most important stage. Next, the show begins. In a special furnace, superalloys are melted, which include nickel, chromium, and other metals capable of withstanding temperatures above 2,000 degrees Fahrenheit. This molten metal is poured into the ceramic mold. But the secret is not only in the material, but also in the way it's done. To make the blade withstand gigantic temperatures and loads, it is often cast as a single crystal. This means that the entire piece of metal has no seams, micro cracks, or different grains, as in ordinary metal. Why is this important? Seams or micro cracks in such conditions are like a minefield. One mistake, and the blade shatters. Single crystals are grown through very slow cooling. The mold with the molten metal is gradually lowered into the cooling zone of the furnace. This process can take several days, but the result is a perfectly strong and durable blade. When the metal cools, the ceramic mold is broken, and the blade undergoes thorough grinding. A special heat-resistant coating may be applied to the surface so that it can withstand extreme temperatures even longer. And so, each blade is checked separately. If there is even the slightest defect, it doesn't go any further. Fuel injection nozzles, combustion chamber parts, or even compressor blades in aviation are made using 3D printing. For example, the company GE Aviation prints nozzles for its engines that weigh 25% less, but are 5 times stronger than traditional ones. Layer by layer, from powder and light, parts are created that allow planes to fly faster, farther, and more economically. First, engineers create a digital 3D model of the part with maximum precision. Here, every curved surface or cavity matters. Why? Because these parts often work in places where a millimeter can change everything, from the engine's efficiency to its reliability. The digital model becomes a map for the 3D printer, which knows where and how to create the required shape. Instead of the usual piece of metal, an ultrafine powder is used here. For example, of titanium, nickel, or Inconel, this is a super aluminum alloy. It looks like sand, but with particles so fine that they are almost invisible to the naked eye. The powder is poured into a special reservoir, and it becomes the building material. The principle of the printer's operation is simple but ingenious. It melts the powder using a laser or an electron beam. The laser heats the powder to such a temperature that it literally fuses into a homogeneous metal structure. Then the next layer of powder is applied, and the process is repeated. This method is called selective laser sintering or melting. And what's cool is that 3D printing allows for the creation of even the most complex geometric shapes. For example, parts with internal cooling channels, which are generally impossible to produce by casting or milling. You know, in traditional manufacturing, you often have to first make a large part and then cut off all the excess. This is not only time-consuming, but also expensive because a lot of material is wasted. But 3D printing works differently. Only what is needed is created without waste. The resulting part is not yet completely ready. After printing, it undergoes heat treatment. It is heated and gradually cooled to relieve internal stresses in the metal. Then comes the final grinding, polishing, or mechanical processing if precision needs to be adjusted. And of course, each part undergoes thorough testing. After all, everything here is serious. If a part does not withstand the load, the consequences can be catastrophic. The engine assembly takes place in a huge hangar, where every foot of space is occupied by tools, engine parts, and people in overalls who are intently working on something extraordinary. This place is the final stage of creating an aircraft engine. Here, individual parts such as blades, compressors, combustion chambers, and casings are transformed into a single whole, ready to lift an airplane into the sky. It all starts with the engine casing, which resembles a giant metal cylinder. This is the skeleton to which all other parts will be attached. The casing is made of titanium or nickel alloys, as it will have to withstand insane loads. Engineers work like watchmakers. The casing is secured in a huge machine tool to ensure everything is perfectly level. Next come the compressors, several rows of blades that are responsible for compressing the air before it is fed into the combustion chamber. The blades are installed one by one, as if decorating a giant wheel. Each one is checked by hand, as the slightest defect can ruin the entire job. After the compressors, it's the turbine's turn. These are the blades that convert the energy of hot gases into motion. The turbines are placed so precisely that the distance between the blades and the casing walls is sometimes measured in microns. Next, the combustion chamber is installed, the real hell of the engine. Here, compressed air is mixed with fuel and burned. Engineers install special nozzles that ensure a uniform fuel supply. And here, everything must be perfect. An incorrect nozzle angle, and the engine can lose efficiency or even fail. A central shaft runs through the entire engine, a kind of backbone. At one end of the shaft, a fan in the form of a huge wheel is attached to the front of the engine. At the other end, the turbine. When the turbine rotates under the influence of hot gases, the shaft transmits this energy to the fan, which sucks in air. Special robots are used to install the shaft. This part of the process requires surgical precision, as even a microscopic misalignment can cause vibrations that will kill the engine. When the internal part of the engine is assembled, the external systems are added. Fuel pipes that supply fuel to the combustion chamber, an oil system that provides lubrication for all moving parts, and electronics, because the engine is literally packed with sensors that monitor temperature, pressure, speed, and much more. These elements are attached using cables, tubes, and bolts that must withstand not only vibration, but also extreme temperatures. After the assembly is complete, the engine is not sent to the aircraft right away. First, it is attached to a test stand, where real flight conditions are simulated. From takeoff to turbulence at an altitude of almost 33,000 feet. This is the most spectacular stage. Starting the engine at full power is accompanied by a roar that can be heard for several miles and bright gas streams. The engine runs under load for hours, and engineers check it for strength, endurance, and efficiency. When the engine passes all tests, it is disassembled, the main components are checked again, and then it is finally assembled. The finished engine is packaged and transported to a Boeing or Airbus factory, where it becomes part of a new aircraft. And so, part by part, engineers create the heart of an airplane, which is capable of carrying thousands of passengers across continents. Isn't that a modern masterpiece? Let me know if you would like to see more videos like this. Every year, over 50 million tons of batteries are discarded worldwide, from small AA batteries to giant electric vehicle batteries. Imagine a mountain of metal reaching the size of Mount Everest, filled with toxic substances. But now, part of this mountain gets a second life. Behind the thick walls of factories, old batteries are put into shredders where steel blades tear them apart. They are frozen with liquid nitrogen and turned into a black powder that will once again become lithium or cobalt. Watch until the end. You will see how a new future for energy is born from waste. Battery collection starts with people. Private individuals turn in batteries from phones and laptops. Car service centers, batteries from electric vehicles, and also businesses that use a lot of equipment. Collection points are in electronics stores, supermarkets, or specialized collection centers. Here, everything is as manual as possible. People bring batteries, and staff or volunteers accept and record them. Old batteries from factories or car service centers are delivered by trucks to large collection centers. Special battery containers have sensors that determine the fill level. When a container is almost full, a signal is sent to the collection company. Some companies use drones to check the fill level of large containers in remote locations. Batteries are sorted by type by people and machines, because batteries come in different types: lithium-ion, nickel metal hydride, lead acid, and so on. They cannot be mixed during recycling. At small collection points, for example, in cities, batteries are sorted manually by workers. They rely on markings, labels, and appearance such as shape and case color. Small batteries from smartphones or laptops go in one direction, and large batteries from electric vehicles in another. At large enterprises, automatic sorting lines are in operation. Machines scan batteries by size, weight, and the type of metals they contain. X-ray analysis or spectroscopy is used to determine exactly which battery is in front of the machine. After scanning, the batteries move along a conveyor to different bins, where they await the next stage. Even at automated factories, people are present. Operators check whether the machines are sorting the batteries correctly. If a problem arises, for example, a torn battery case or a missing label, people intervene and sort manually. Batteries from electric vehicles or solar stations are too large for automatic lines. This is where robots come into play, helping to disassemble these giant blocks into smaller sections. Then they are sorted by material. No matter how much machines do, people are still the most important in the sorting process. These are mainly the workers at collection points and the operators of sorting lines. Specialists assess damaged batteries manually because machines cannot yet recognize all defects. Machines work faster, but for now, they can't do without people. Ultimately, every correctly sorted battery is a chance to recover rare earth metals and reduce environmental harm. Next, the batteries need to be shredded. They enter real metal jaws. The batteries are loaded into a machine that looks like a huge shredder, equipped with steel blades. The blades are so powerful that they can even shred the body of an electric car. Metal chaos ensues. The sound of tearing, grinding, and cracking. The batteries are literally ripped to shreds. Since the batteries can be charged, they first undergo freezing in liquid nitrogen. This cools the metals and reduces the risk of ignition. Some shredders operate in sealed chambers with inert gases to exclude contact with oxygen. There is also a more spectacular option. In some places, a controlled current is first used for ignition. The battery literally burns out, leaving only the metals. The batteries are shredded into pieces from a few centimeters to a crumb, depending on the type of shredder. The blades rotate at a speed of over 2,000 revolutions per minute, and metal fragments fly in all directions with a clang inside a protected chamber. The shredded pieces pass through magnetic separators, which with filigree precision extract ferromagnetic metals, for example, nickel or cobalt. Fragments of other materials continue their journey along the conveyor. A fine black powder, known as black mass, settles in special containers. This is where the treasures are hidden: lithium, cobalt, manganese. Machines literally suck up the powder with dust collectors to gather even the microparticles. Residues that are not suitable for recycling, meaning plastic and traces of electrolytes, are washed away with special streams of liquid. At this stage, hydraulic crushers are used, which turn the remnants into a slurry that is easy to filter. Engineers monitor the condition of the shredders and the temperature level inside the chambers. Specialists work with the results of the shredding. They check whether all the metals have been separated and whether any extra impurities remain. If a battery is charged and has defects, it can literally explode during shredding. But the system controls this. The explosion is extinguished by gases, and the process does not stop. After the batteries are shredded and that precious black powder is obtained, science in action, as they say, begins. The metals that seem to be hidden forever are extracted using two main methods: hydrometallurgy and pyrometallurgy. And although this may sound a bit technical, the processes themselves are extremely interesting. So what does it look like? Battery fragments are immersed in special acid solutions. There are huge tanks where a yellowish-green liquid is bubbling. This could be sulfuric or hydrochloric acid. During immersion, a reaction occurs. Lithium, cobalt, nickel, and other metals literally dissolve in this soup. To extract the desired metal, a clever trick is used: ion extraction. Special reagents, for example, organic compounds, are added to the liquid, which capture a specific metal, like a magnet. As a result, each metal settles into a separate layer. When the metals are separated, they are precipitated in the form of salts or hydroxides. They look like small white or colored crystals. For example, lithium precipitates as lithium carbonate, a powder that looks like fine sugar. Cobalt becomes a bright blue precipitate, and nickel, a pale green one. If hydrometallurgy is a gentle approach, then pyrometallurgy is more like shock therapy for metals. Here, everything literally burns and melts. The black mass is loaded into a huge arc furnace, where the temperature reaches almost 3,000 degrees Fahrenheit. The metals melt into a liquid mass, and the plastic and other residues simply burn up. The metals stratify like oil and water, but at the temperature of molten lava. Several layers form in the furnace. Heavy metals, meaning cobalt and nickel, settle to the bottom, while lithium remains in the slag. This is the upper, lighter layer. Then this slag is broken up and processed separately to extract the lithium. After cooling, the metals take the form of small ingots, shiny, smooth, and ready for reuse. The cooling after the pyrometallurgical process usually happens in a controlled manner. After all, if you just let the molten metals cool on their own, it could take hours and sometimes even days. In addition, such cooling can create an uneven metal structure. This will affect the quality of the final product. Therefore, they are usually cooled in special chambers, where the cooling rate can be regulated. If the controlled cooling is air-based, the ingots are left on a conveyor under powerful fans. It's like a giant hairdryer that quickly cools the metal surface. If it's water cooling, for a faster process, the metal ingots can be immersed in a bath of water or special liquids. This is a huge tank where the red-hot ingot, upon entering the water, releases clouds of steam. It looks quite spectacular. Sometimes there is combined cooling. This is when some stages begin with air cooling and then are completed with water cooling to reduce stress in the metal. Controlled cooling ensures a uniform structure of the metals, which is critically important for their reuse in batteries. This reduces cracks or defects that can arise from sharp temperature changes. The obtained lithium is used to create new batteries, those that will charge electric cars or even your phones. Nickel can become part of turbines that generate energy from wind, and cobalt, an important component of medical equipment. So we are literally closing the loop. Old batteries give life to new technologies. Discarded batteries can turn into a real environmental disaster. First, they contain toxic substances that pollute the soil and water. Second, the mining of new rare earth metals not only depletes natural resources, but also harms the environment. Recycling solves both of these problems. You know what else is cool? The more batteries we recycle, the less we depend on mining new materials. This is a direct path to sustainable development. Despite the popularity of lithium, only 1% of this metal is currently recycled. The main reason is the high cost and complexity of the process. But researchers are developing new technologies that could change the situation in the coming years. Interestingly, even now, electric car manufacturers like Tesla, Volkswagen, and BMW are investing in their own recycling plants to maintain control over valuable materials. Every year, over 1 billion feet of steel chains are produced worldwide, from those that lift sea cranes to those that support bridges. But only a few of them go through a journey where precision is measured in microns, and every spark during welding is the beat of a metal heart. Imagine, a piece of ordinary steel transforms into a link capable of withstanding tens of tons. How exactly? In a few minutes, you will see how a force that cannot be broken is born. And if you watch until the end, you'll learn the secret that determines whether a chain will survive under maximum load. Our journey begins not in the noisy workshops, but much earlier, in the design office. It is here, at the design stage, that engineers determine what our chain will be like. What is it intended for? What loads must it withstand? Will it operate in an aggressive environment? The answers to these questions dictate the choice of material. In the vast majority of cases, for the manufacture of welded chains used in lifting mechanisms, industry, construction, or as fastening elements, we use high-quality steel rod. Take a look at these warehouses. Here they are, our round bars, thick, heavy, shining with strength. They can have different diameters, from a few millimeters for light chains to tens of centimeters for true giants that lift tons of cargo. Each batch of rods undergoes a thorough incoming inspection. The metallurgical laboratory checks the chemical composition of the steel, its mechanical properties, tensile strength, impact toughness. This is critically important, as the safety and reliability of the final product depend on the quality of the raw material. Only rods that meet the highest standards are allowed for further processing. This is the first, but extremely important, step in ensuring the unsurpassed quality of our chains. So, our selected steel rod is ready for transformation. The next stage is cutting. Here, high-precision cutting machines come into play, which, like surgeons, cut long rods into sections of a perfectly specified length. These sections will become our future links. Every millimeter matters, as the uniformity and correct geometry of the entire chain depend on the cutting accuracy. Operators carefully monitor the process, controlling the dimensions of each blank. And now we move on to one of the most spectacular stages: forming the link. Look at this powerful machine. It's an automatic press or a special bending unit. The metal section, heated to a plastic state, and sometimes without preheating if the diameter and steel grade allow, is fed inside, and under colossal pressure or a complex bending motion, it is transformed. Before our eyes, a straight rod is bent into a perfect oval or round shape, the future link. It is important that the ends of the rod are not completely joined, leaving a small gap, a seam. This seam will be a key element for the next stage. The newly formed link is fed to a mechanism that threads it through an existing link of the chain. It's like an amazing dance where one part is woven into another, creating a single whole. And now, the most important moment: welding. Most often, electric resistance welding, or flash butt welding, is used for chains. This is a high-tech process where the ends of the link that form the seam are clamped between electrodes. A powerful electric current is passed through them, which instantly heats the metal to its melting point. See those bright flashes? The fountains of sparks? That's the metal melting. And then under the pressure of the electrodes, an upset occurs. The ends are joined, forming a strong, homogeneous weld. In some cases, especially for very large chains, arc welding may be used, but the principle remains the same, creating an unbreakable metal joint. This weld is not just a connection. It's the weakest point of the link, and it is here that its future strength is established. Welding masters are true virtuosos, as the integrity of the entire chain depends on their work. After welding, the excess metal can be trimmed or processed for smoothness. The newly formed and welded chain, although strong, has not yet revealed its full potential. To meet the highest requirements for strength, durability, and safety, it goes through a series of finishing processes. The first of these is calibration. The long chain passes through special dies under pressure. This ensures the precise dimensions of each link, eliminates minor deformations after welding, and gives the chain uniformity. A calibrated chain will be ideal for working with sprockets and other mechanisms where precision is critical. After calibration, the chain heads to the heart of the factory: heat treatment. This stage is one of the most important and determines the final mechanical properties of the chain. Depending on the steel grade and desired characteristics, the chain may undergo several operations. Let's talk about each of them separately. Quenching. The chain is heated to a high temperature in special furnaces and then rapidly cooled in water, oil, or a polymer solution. This makes the steel very hard but brittle. Tempering. To eliminate the brittleness after quenching and increase the ability to absorb impact energy without breaking, the chain is heated again, but to a lower temperature and cooled slowly. This process gives the chain the necessary balance between hardness and ductility, normalizing. Sometimes, instead of, or in addition to, quenching and tempering, normalizing is used, heating to a certain temperature, followed by cooling in air. This improves the metal's structure and relieves internal stresses. All these processes are carefully controlled by computer systems, as even a small change in temperature or holding time can significantly affect the final result. Heat treatment is a true art of controlling the properties of metal. After heat treatment, the chain comes out of the furnace, but its journey is not yet over. At this stage, it may have scale on it, a layer of oxides formed at high temperatures. Therefore, the next step is cleaning. This usually happens in special shot blasting chambers. Thousands of small metal shot particles under high pressure bombard the surface of the chain, knocking off scale and other contaminants. The result? The chain becomes clean, smooth, with a pleasant metallic sheen, ready for the next stages. In order for our chain to serve long and reliably even in difficult conditions, it needs protection from corrosion. This is where coating comes into play. The most common method is galvanizing, which can be hot dip or electroplating. In hot dip galvanizing, the chain is immersed in a bath of molten zinc at a temperature of 860 degrees Fahrenheit. Zinc, interacting with steel, forms a strong protective coating that not only prevents rust, but also has the property of self-healing for minor damages. In electroplating, the chain is placed in an electrolytic solution, and under the action of an electric current, zinc deposits on the surface of the steel. This coating is thinner, but gives the chain a more aesthetic appearance. In addition to galvanizing, other types of coatings may be used. For example, polymer paints or special anti-corrosion compounds. Depending on the purpose of the chain, we are approaching the final stage, and this is perhaps the most responsible moment: testing. It is here that our chain confirms its readiness to perform the most complex tasks. Every single chain undergoes a whole complex of checks for compliance with international safety and quality standards. Look at this huge test stand. Here the chain is subjected to colossal loads. It is stretched with a great force, which significantly exceeds its nominal working load, but at the same time does not reach the breaking point. This is the so-called proof load test. During this process, possible hidden defects and weak points that could manifest during operation are revealed. If the chain successfully passes this test, it means that it will withstand the declared loads and ensure safe operation. In addition to this, other types of control are carried out. Specialists carefully inspect each link for cracks, deformations, quality of welds, and coating. With the help of special calipers and measuring instruments, the compliance of the link sizes, their shape, and the chain pitch with the specified parameters is checked. From each batch of chains, samples are taken, which are then subjected to breaking tests. This allows to determine the maximum breaking force that the chain can withstand and to make sure that it meets or exceeds the established norms. These are brutal but necessary tests that guarantee that the entire batch of products is reliable. Only chains that have successfully passed all stages of quality control without exception are given the right to leave the factory premises. Each batch is accompanied by a certificate of conformity, which confirms its characteristics and the passing of all tests. This is our guarantee, a guarantee that you are getting a product of the highest quality and reliability. And now, dear viewers, we see the final result. Chains of different sizes, diameters, with different coatings, neatly laid in coils, ready to be sent to all corners of the world. They will go to the construction of skyscrapers, to port cranes, to ships, to agriculture, to production lines, everywhere where unbreakable strength, reliability, and safety are needed. From small, elegant chains for decorative purposes to huge ones that lift bridges, each of them has gone through a long and complex path of transformation, from raw metal to a high-tech product.